Okay, so let's talk about nuclear chemistry. So by nuclear chemistry, we're ranging into something totally different from what we've talked about before. So this is very different from the chemical reactions we've talked about before. So a nuclear reaction, so we're almost having to completely redefine how we're talking about chemistry here. So this is a reaction in which that involves changes to the nucleus. So before, when we talked about reactions, we're talking specifically about the electrons only. Now we're actually talking about the nucleus. This is something we haven't ever really had to consider before. So this is totally apart from what we consider to be ordinary chemical reactions. Ordinary chemical reactions concern themselves with the arrangement and the movement of electrons, and now we're dealing with nuclear things, talking about protons and neutrons changing. And so remember, we talked about isotopes before. So this is a term we've used before where we talk about two isotopes are atoms of the same element that have different mass numbers, but we're going to actually need a more general term now. The more general term is nuclide. So it sounds kind of weird, but nuclide is just an atom, a specific atom with a specific mass number and a specific atomic number. So just any atom, and we're talking about a specific atom with a specific element with specific mass number. So an example of a nuclide would just be if I said O, and it has to, because it's oxygen, it has to be 8, but I could say O8, 16, or I could say, I've got to find something that's actually plausible. Need to look at the periodic table here. So Ga, gallium, 3170. So these are both nuclides. I'm just talking about the atom and how many protons and how many neutrons it has. That's it. So specific mass number, specific atomic number. So in nuclear chemistry, what we're really interested in is the protons and the neutrons. We don't really care about the number arrangement of electrons, which is a drastic shift from what we've talked about before. Now we just care about protons and neutrons. That's all I care about. So here's a nuclide. I've showed you before. There's 3 different ways to represent it. One is with this notation we've seen before. But this time when we're talking about nuclear chemistry, you're not going to see charges show up because we actually don't care. We just don't care. We care about how many protons and and its mass number, so number of protons, or rather, and in nuclear chemistry, not so much protons, but nuclear charge, which usually is the number of protons, right? So the nuclear charge, so we have a +7 charge, and we have 15 things in the nucleus, so 7 of them are protons, and the other 8 are neutrons, right? It can also be denoted as nitrogen 15, so nitrogen with a mass number of 15, or N15. Either way is fine. We can group nuclides into 2 broad types: stable and unstable. Stable nuclides have stable nuclei, and they don't undergo any sort of change. Unstable nuclides undergo some sort of spontaneous change. Now, most of the time in this class we've dealt with stable nuclides because we haven't wanted to deal with things changing their nucleus. But now we're going to talk about unstable nuclides. So it's not true. I've always talked about the nucleus as though it's totally inert, it doesn't do anything. And that's not 100% true. You can have nuclides that don't have nice stable nuclei. When you have unstable nuclides, they undergo radioactivity. So this is the result of an unstable nuclide. It changes, it falls apart, and it radiates spontaneously from this nucleus. So a radioactive nuclide is one that's unstable and falls apart or otherwise changes. I keep saying falls apart, but it just sort of, it's unstable and it changes and it emits radiation. We also call these radionuclides. So radionuclide is just short for radioactive nuclide, which is an unstable nuclide that emits radiation. So we have naturally occurring radionuclides for 29 of the 88 naturally occurring elements. We can make radionuclides for any element in a lab. We can put together a very unstable nucleus for just about any element. And notice there's a lot more than 88 elements on the periodic table. And I'm actually going to talk about how we got those. And it's from making these unstable elements. So a lot of them are man-made through what we'll talk about as bombardment reactions. Okay. So there's no simple rule for determining which nuclides will be stable. But there are some general observations. Any nucleus with 84 or more protons is basically unstable. So if you get up past bismuth, which is our last stable nucleus, we don't really have anything that's stable after that. No naturally occurring element with a higher number of protons is stable at all. Now, unstable doesn't mean it doesn't exist. It just means it's radioactive. And these can be radioactive just like rust, iron rusts, right? In a way, iron is chemically unstable because it rusts in water, but it takes a long time to do it. In the same way, you can have elements that decompose, their nuclei decompose slowly. So they still exist, they just slowly are falling apart. So there's also a correlation between the stability and the neutron to proton ratio. Now, you may look at the periodic table and think, oh, well, it's 1-to-1. If you have 8 protons, you need 8 neutrons, right? And so for oxygen, its stable nucleus, or its stable nuclide has mass number 16. For carbon, the stable nuclide has mass number 12, right? This is true for small elements. For small elements, it's true that the stable ratio is close to 1-to-1. But once you get a little bit bigger, it gets closer to 1.5-to-1. I'm actually going to show you an image here. Okay, so I just found this image on doing a Google search, and it's a pretty cool image. This shows the number of neutrons and the atomic number. And this line, the dark heavy line, is 1-to-1. It's a 1-to-1 ratio. So down here it's small, and these are plotted dots for all of the stable nuclei. So notice what happens. Down here at 10 protons, and even up to about 20 protons, we stay close to the 1-to-1, but pretty soon we go zooming off up a little high, needing more neutrons. Because remember, protons are positively charged and we're packing them in there. So it gets very complex, but you can think of neutrons as sort of the padding and the glue that kind of holds the protons together. When you cram that many in there, you need more and more neutrons. And eventually, you get up to 84, and there's just no way to pack that many protons together that's stable. So, and then we have a lot of unstable naturally occurring elements, and they typically occur through supernova. So yeah. So you can kind of see visually that the stability actually isn't 1-to-1 always. It is at small atoms. There we go. So, there we go. Sorry, a little bit of a hiccup. So, radioactive emissions. There are 3 types of radioactive emissions. There's more radioactive things that happen, but we're going to stick to these 3 basic ones. Alpha, beta, gamma rays. So, alpha rays are made up of alpha particles, beta rays are made up of beta particles, and gamma rays are actually just gamma rays, weirdly enough. So alpha particles are particles that have 2 protons and 2 neutrons. So this is one of the types of emissions. So when a nuclide is unstable, it will sometimes spit out alpha particles. And it's doing this just to get smaller. Because notice it's shedding 2 protons and 2 neutrons. So if we think about that stability band, right, where it was kind of like this, it's kind of going up here. Well, this just moves you back this way straight. Wherever you are, it just moves you at a 1-to-1 rate, shedding 2 protons and 2 neutrons. So that's an alpha particle. We sometimes represent it as a helium nucleus because that's what it is. 2 protons and 2 neutrons is just a helium-4 nucleus. Beta particles. This is another type of emission. Now it's important for me to make clear that beta particles are emitted from the nucleus. Because a beta particle is functionally the same as an electron. But it's coming out of the nucleus. Right? It's coming out of the nucleus. So, and I'll get to when I talk about these more specifically and how to write the equations, I'll show you why this is even possible. But you get something, notice we have no mass, right? Because it's like an electron. It has no mass number, because it's not a proton, it's not a neutron. And it's got a -1. This is why I say this isn't exactly atomic number. It's more nuclear charge. So this thing has a -1. Well, it's negatively charged. The nucleus is kicking something out that has no mass, but it has a -1 charge. Right? And the last thing is a gamma ray. And gamma rays are just high energy radiation without mass or charge. They're electromagnetic radiation. So like light or microwaves or anything like that, but very high energy. Okay. So I'm going to talk about how to write equations for these kinds of decay. So radioactive decay is the process where a radionuclide, remember, a radionuclide is a nuclide that is unstable and falls apart, emitting radiation, is transformed into another element. So we actually are changing from one element to another and emitting radiation in the process. So it's going to be one of the three types of radiation we talked about. Now, there's two terms that are important here. Parent nuclide. Think of parent nuclide for these kinds of reactions as the reactants. They're what we start with. They're the thing on the left side of the equation. So it's what undergoes the equation. And the daughter nuclide is what we end up with. It's the product. So let's talk about nuclear equations. And then I'll talk more specifically about alpha particle decay. So here is a generic form for an alpha particle decay. But more importantly, this is a good introduction to nuclear equations. Something that's important about nuclear equations. What we're showing, so here on the left side, this is the parent nuclide. It's like the reactants. Over here is the daughter nuclide. And this is the emission that's happening, the alpha particle emission that is happening in the process. So we start with just this nucleus, and it falls apart to something else and spits out an alpha particle as it happens. So when we write these kinds of equations, this is not exactly, it looks very similar to a chemical reaction, but it's not exactly. There's some important differences. One, the symbols we're writing are just for the nuclei, not the atoms. We're not considering the electrons at all. There's nothing happening with the electrons. We're not messing around with the electrons. We are just talking about the nuclei. So the charges aren't even, we don't care. The mass numbers, before we would sometimes omit the atomic numbers, we always include the mass and the atomic numbers. Always. So we have both. And the elemental symbols are not going to be the same thing. Notice this is X and this is Y. The whole point is, this is one of the nuclear reactions, and basically the only way we can turn one element into another element. So the balancing isn't going to be the same as for chemical reactions, because remember, for chemical reactions, we have to have the same number and type of atoms. Well, the exact nature of the atoms are going to be different, but we are going to make sure we have the same number of protons and neutrons. Right? So to balance a nuclear equation is a little bit different. A balanced nuclear equation, the sum of the superscripts on both sides of the equation are equal, and the sum of the subscripts are equal. So if we go back here, we have x equals a, right? And then we have a minus 4 plus 4 is a. Z minus 2 plus 2 is z. So they have to add up, right? So what's the sum of everything in the subscripts on the right side has to equal the sum of the subscripts on the left side, and the superscripts, I switched the word super and subscript, but I think you get my meaning. Up here, everything has to add up to be what's over here, and down here, everything has to add up to be what's over here. Okay, I'll show you some examples. So let's talk about alpha decay, actual real-life examples. So I have bismuth, right? Bismuth with an atomic number of 83 and a mass number of 221. And I think I wrote that incorrectly. I did write that incorrectly. I made a mistake. Let me fix that right now. Okay, there we go. So it should be 211, not 221. So bismuth 211, right? And so what happens is it emits an alpha particle, right? So it kicks out 4 neutrons, or not 4 neutrons, sorry. It kicks out 4 nucleons. 2 of them are protons, the other 2 must be neutrons. But the point is, because it's kicking out an alpha particle with a mass of 4, the mass of the daughter nuclide is 4 less. So 211 minus 4 is 207. 83, the charge, 83, we're kicking out 2 protons, so its charge is going down by 2, so 81. So this becomes our new nuclide, so this is our daughter nuclide. Let's make sure I didn't make a mistake over here. It looks like I didn't. So I have uranium-238 kicking out alpha particles, so it's emitting an alpha particle, so its mass number goes down by 4, and its atomic number goes down by 2. Okay? So hopefully that's making sense. We'll do a little more practice with these. Beta particles. Okay, so beta particles. Here's beta decay, beta emission, right? So again, everything has to add up. So I have my parent nuclide. The mass number isn't changing because what's being emitted has no mass, right? So the mass stays the same, but I'm emitting something negative. So my mass, my charge is increasing. The charge of my nuclide is increasing. So my daughter nuclide actually has a greater charge than this. So this actually, if you look at that IL stability, this kind of decay, so if we have something like this kind of decay moves us, right? It doesn't change. So remember, this is number of neutrons, and this is number of protons, right? So I stay the same vertically, but my number of protons actually goes up. So I go, so this is how usually things that are down here get back into that band of stability there. So here's some actual examples. So beryllium, beta decaying into boron, right? So really small nuclides, you want an equal number of protons and neutrons. This has too many neutrons and not enough protons. Beta decay, now I have the right number. This one, beta decay, my mass number doesn't change, but my charge increases. My atomic number goes up by 1. Okay, how is this even possible? This almost doesn't really make sense. Trying to think about this in real terms, this is probably really maddening and very weird and confusing. So remember, this probably even makes it more confusing that this particle is being ejected from the nucleus. This isn't like an ion forming. This isn't an electron cloud. This is actually coming out of the nucleus, and when you think, now we haven't talked about this, protons and neutrons are actually made up of smaller bits, so you can actually mess around with them a little bit. So here's what's actually happening. A neutron is actually falling apart into an electron and a proton. So what's happening is, when you kick out a beta particle, when you have beta decay, you actually are turning neutrons into protons. That's what's happening. So you're taking what was a neutron and you're turning it into a proton because we had too many neutrons and not enough protons, so let's just co-opt a neutron and turn it into a proton. All right. Okay, last type of emission, and that is gamma ray emission. Now gamma ray emission, you guys are going to like this one, it's easy. Gamma rays are neutral, and they have no mass, and they're just energy. Gamma rays only ever can occur along with alpha or beta particles, at least naturally. We can, in the lab, make pure gamma emitters, but naturally that doesn't happen. So because gamma rays, their symbol is gamma 0, 0, they don't affect the balancing of the nuclear equation, we usually leave them out. I should say, not every alpha or beta emission is going to have gamma rays with it, but some do, and we usually leave them out because they don't matter, they don't affect anything, right? So we go down by 4, we go down by 2, and then the gamma doesn't mean anything, so we often just leave it out. We just omit it. So that's that's equations, writing equations. Let's do a little, okay, so here's a couple practice problems. So write a balanced nuclear equation for the alpha decay of each of the following, and then for the beta decay of each of the following. So I want you guys to try this, and then I will do these. So pause it and try it. Okay. So curium. What we're going to have to do here is we have to actually look up, and I don't happen to know. I don't use curium that much. I don't work with curium that much. So I'm going to have to look up what is curium, what's the atomic number of curium. So I'm going to look it up, and it looks like it's 96. So we have Cu, I think it is. I'm going to double check because I don't use it much. Oh, Cm, sorry. Cm 96 240. I'm going to double check so I don't make a mistake. Check my list one more time. Yep, 240. Now, we're going to undergo an alpha decay. So, on this side, we're going to write an alpha particle. Alpha particles are always the same. So, our parent nuclide is curium-240. So, the daughter nuclide, now here's how I handle this. I say, okay, well, this has to go down by 4. So, this has to be 236. It must be. And now, and the atomic number has to go down by 2 because we kicked out 2 protons. So, it must be 94. So now I'm going to look up what is atomic number 94, because I don't happen to know. It looks like it's Pu, which is one of those things I don't use much. It looks like it's plutonium. So we have plutonium. There we go. And no, I do not expect you to know the names of these elements. I don't know the names of these elements. I look them up as I need them. So here we go. This is, I think, do you remember if this is thorium or thulium? This is a little bit of an education for me. Thorium. So we have 90 and then 229, and it's going to undergo alpha decay. So 4 and 2, always the same. So my mass number goes down by 4, must be 225 now, and becomes 88. So I can look up what's atomic number 88, and it looks like atomic number 88 is radium. Okay? Beta decay, carbon-14, this one I actually know. And we emit a beta particle, which is always 0, -1, so it becomes 14, and then 7, which makes it our daughter nuclide, nitrogen. Right? So hopefully what you're getting out of this is the way I'm figuring out what the new element is I'm just doing the math. I'm looking at how my atomic number changes, right? So I kicked out a beta particle, a neutron became a proton, so now I have nitrogen. So notice how we went from an unstable carbon atom, or carbon nuclide, to a stable nitrogen nuclide. So now we have germanium, 3277. We're going to undergo beta decay, -1. So I get 77 is still my new, and then I have 33. So what's 33? I believe it's arsenic. So arsenic. Hopefully that makes some modicum of sense.